we can look at an even more graphic presentation of polarized electromagnetic waves by looking at light. So here's an overhead projector, and it has some intensity displayed on the wall when it's just light coming through. But remember, this is random light from a bulb, so each photon has a different polarization, and they're all just randomly oriented. So every possible polarization is coming through here. And I'm going to take a polarizer and put it on that. This is just a sheet of Polaroid material, the commercial material. And similar to your sunglasses, this is made with stretched polymers. So instead of those metal lines, now we stretch polymers that conduct, and they will block the electric field along the direction of conduction and let it through the other way. So let's put one on. There it is with the polarizer. There it is without. And as you can see, it cuts down on the intensity. And what we learn is that it cuts the intensity exactly in half. That is, if you polarize the light, it lets through everything going one way, blocks everything going the other way. If you want to think about it another way, you could say it lets a component of the electric field through at all these different orientations, and it only lets the component through that's along the polarization direction. So it chops off the component. If you average that component over all angles, you get a half of the intensity. That is, the average is at 45 degrees. So the average electric field component will be the cosine of 45 degrees, root 2 over 2 down, and the intensity goes like the square of the electric field. So that root 2 over 2 squared gives us that factor of a half. So the only things that are really critical to know about polarization is, one, when you go from unpolarized light to polarized light, the intensity is cut in half. And then the second thing is, now that you have polarized light, what happens when you pass it through a second polarizer? So here's a second polarizer at an angle of about 45 degrees. If we orient it the same direction as the first polarizer, then all of that first polarizer's light gets through. We have the original intensity cut by half. But now if we rotate it, it gets cut down by the square of the cosine of the angle, Malice's law, cosine squared theta, until theta is 90 degrees, and then it cuts the light out completely. So now we have one polarizer only letting through, say, one orientation of the electric field. The other polarizer is only letting through a perpendicular orientation. We call these crossed polarizers, and so they let no light through. But one of the most unusual situations in physics is this one. We have two things, and they don't allow any light to get through, but I can take a third thing and put it in the way, and look what happens. I'm putting something in the way of this light, and yet now it's allowing some of the light to get through. Of course, if I orient it right along one polarizer or right along the other polarizer, then it'll just be repeating their effect. But in between, it lets it through. How is that possible? Well, it's all due to the components of the electric field. The first polarizer lets it through vertically. This little one I've inserted at 45 degrees chops off a component of that. So out of this full field, only a little component will get through. And now the third polarizer that was there, that was at 90 degrees, will chop off a component of that and only let a little bit through. But now those two components are non-zero. There will be an appreciable component left, as you can see. So it's one of those unusual situations in physics where you put something in the way, but it lets something through instead. So polarized light is used a lot in microscopy and in engineering to study structures in an indirect but fairly visible way to see the effects, say, in this case, of stress on the material.